here with chapter 24. And for chapter 24, we are going to talk about something related to potential and storing energy, which is capacitance and dielectric. Capacitors are really devices that they are really widely used in all electronic devices. Most of the applications that we have now contain capacitors. We are going to today understand and find out what is really the nature of capacitors and how to calculate a quantity that measures their ability to store charge. We use them to store charge, and we will see how we can increase that, or just what are the factors. How to analyze capacitors connected in a network. We are going to start now connecting electronic components in a network. One example is how to connect capacitors, and in the future chapters we will learn how to use also resistors, and also later we will combine all of them together. And here there are two major methods for connecting. One of them we call it in series, and the other one we call it in parallel. And we are going to, find out about this. How to calculate the amount of energy stored in a capacitor, and how we can actually make the capacitors more effective by adding dielectrics. And finally, we will learn how to use Gauss's law when dielectrics are present, and we will solve, of course, problems on each of these. Now you can see this guy in the picture using a phone to take pictures, and you can see the flash in photography that is used. The energy that we use to operate this flash is stored in a capacitor. And I will say, simply the capacitor is two closely spaced conductors that they carry opposite charges. We store energy in a capacitor using the electric field that is produced. Now, capacitors here, we are talking about any two conductors separated by an insulator or vacuum. We're going to start first with vacuum, and we call that a capacitor. And when the capacitor is charged, these two conductors, they will have two equal charges in magnitude but opposite in sign. Then one of them is positive, one of them is negative, and the net charge on the capacitor as a whole is zero, because equal charges, one of them is positive, one of them is negative. I will say one common way to charge a capacitor is to connect the two conductors to opposite terminals of a battery, and then actually the capacitor is gonna charge, and that is gonna create a potential difference VAB between the conductors, that they are really equal to the voltage of the battery ideally. And if we change the magnitude of the charge on each conductor, the potential difference will change, but the ratio is gonna stay the same, because that ratio, it is called capacitance. Then capacitance can be calculated as Q, which is the magnitude of the charge on each conductor. Not you don't add the two charges, it's just one of them. The magnitude divided by the potential difference between the conductors. One of them, of course, having a charge plus Q, and the other one having a charge which is a negative Q. One of the most, we have, of course, different shapes and different, even with industry, they are made of different materials. The most, I will say, common capacitor that we are using, called parallel plate capacitor, which is consisting of two parallel conducting plates. separated by a distance, and that is really that distance is small compared to their dimension. Like, the areas are really big, and that D is small. And then by charging one of them plus Q, the other one negative Q, and we are going to have a potential difference VA between them. Now the field, we know from previous chapters that the field between the plates of a parallel plate capacitor is uniform, and the charges are uniformly distributed over their opposing faces or surfaces. And when the region between the plates doesn't have any dielectric, means it's vacuum, we're going to have C equals Q divided by VAB, and then the magnitude of the capacitance is going to be just the electric constant epsilon 0 multiplied by A over D. Then it depends on, I will say, the geometry of the capacitor. A, it is the area of each plate, and D is the separation or the distance between the two. Then the capacitance depends only on the geometry of the capacitor. It has nothing to do with other factors. The quantities here, A and D, are really the area and the distance, and they are constants for a given capacitor. And of course, epsilon 0, it's the same constant that we are using always, which is epsilon 0, the electric constant. This is like another application here, condenser microphones. Inside a condenser microphone, there is a capacitor with one rigid plate and one flexible plate, and the two plates are kept at a constant potential difference, and sound waves cause the flexible plate to move back and forth by vibration, because remember, sound is creating vibration, and that is making the capacitance C change and causing charge to flow to and from the capacitor. And thus, I will say this the sound wave is converted to a charge flow that can be amplified and recorded digitally. Now the SI unit that we are using for capacitance, it is the farad. We use for it uppercase F, and that equals Coulomb divided by volt, or like here it is Coulomb squared. This is Coulomb squared divided by Newton meter, or Coulomb squared divided by joules. 1 farad, actually, it is a very large capacitance. We don't have like if we want to have one, maybe it's going to be as big as the room if it is 1 farad. Therefore, we use for commercial capacitors microfarads, which is 10 to minus 6, picofarads, nanofarads, because, but usually I will say microfarads, which is 10 to minus 6. Now, we want to learn how when we connect capacitors in networks. One of them, it is the series one here. For this section, it's very important to understand the following points. First, I will say the two capacitors, when they are connected in series, they are connected one after the other, which means if like a capacitor, I will assume, have 2 hands, 1 and 2, and the other one has 2 hands, 1 and 2, then my hand number 1 is gonna be connected to the battery, okay, and I will say, and hand number 2, it is connected to hand number 1 of the second one. And then the hand number 2 for the second one, it is connected to the battery or to the voltage source. Now we can, when we talk about equivalent capacitance, means that I will replace my capacitors with a single capacitor. And how we are going to calculate this, when they are in series, this is also one important thing that you need to know, that the two capacitors in series connection, they have the same charge. Okay, if the one of them is holding 80 microcoulombs, the other is going to have 80 microcoulombs. They are going to share the voltage. This a piece of information, it is very important when you solve. Now, I will say, we can say that C equivalent is going to be having Q over V, which is Q is the total charge divided by V, which is the total voltage. And therefore, we can derive here that based on, I will say, let me write this here, V total is V1 plus V2, and therefore let me add a page here. V is a Q over here, I will move from here to here. This is Q over what is called C equivalent or C total, and that is Q over C1 plus Q over C2. And then since it is the same Q, we can cancel. Then if you have two capacitors that they are in series, you're going to say 1 over C equals 1 over C1 plus 1 over C2. I will say usually I will have this decimal, this is decimal, I add the two decimals, and then I will take 1 over that number to get C. For example, let's say I have one of the capacitors is 4 microfarads, and the other one it is 8. Sometimes we are going to give you numbers that they are really easy to use, but not necessarily. Like, okay, 4 microfarad here plus 1 over 8 microfarad. I like to use kind of the things that like decimals and add them. Sometimes you will realize the relation, then it's easier, but I want to have general. Then I will find 1 over 4, which is 0.25, plus 1 over 8, which is 0.125, and that is microfarad minus 1. And then when you add these, you're gonna get 0.375, and then take 1 over this number. You're gonna get that C equivalent is gonna be 2.67 microfarad. Actually here also what I can do, okay, just to verify, I can have, this is 2 over 4 plus 1 over 8, 2 over 8 plus 1 over 8, and that is going to be 3 over 8. Then my C equivalent is going to be 8 over 3. And if I divide, just like, because I have easy add in friction here, add in, I will say, fractions. Yeah, then it is 2.67. All right, also when several capacitors are connected in series, the magnitude of charge is the same on all plates, all the capacitors. The potential differences of the individual capacitors add to give the total voltage, and therefore we can find that 1 over C equivalent, it is 1 over C1 plus 1 over C2 plus 1 over C3. We are going to see that this is different from when we have resistors. Actually, the two cases will be switched around. Now, capacitors in parallel, which is now my hand number 1 is connected to the hand number 1, my hand 2 is connected to my hand 2, and here they have the same voltage or the same potential difference. and the charge here is going to be different. The total charges, Q is going to be Q1 plus Q2, and therefore we are going to find that C equivalent is going to be C1 plus C2. Then you add it, and then you are going to say this in general. If I have several capacitors connected in parallel, then a Q total, it is Q1 plus Q2 plus Q3, and then C equivalent is going to be you add all the capacitance. Most of the time, of course, we don't have that. We have a combination of resistors that they are going to be parallel, some of them and some of them series, and then we have to work on that, and we will see how we are going to work on these examples later. Energy stored, of course, as I said before, we use capacitors to store energy, and the energy stored in a capacitor, we are going to use for it U, not E. E, it is used for electric field, and it is a Q squared over 2C, or if we want to use the equation that Q equals CV, is going to be 1/2 CV squared, or 1/2 Q times V. Now, we also, I will say, the capacitor energy is stored in the electric field between the plate, and the energy density, we call it lowercase u. This is going to be 1/2 epsilon 0 times E squared. And we call this electric energy density in a vacuum. Now, then we don't have any dielectric between the two plates. 1/2 epsilon 0 E squared. Energy stored in a capacitor. A practical application of capacitors is their ability to store energy and release it quickly. An extreme example of the same principle is the Z machine at Sandia National Laboratories in New Mexico, which is used in experiments in controlled nuclear fusion. And the C machine uses a large number of capacitors in parallel to give tremendous equivalent capacitance. And I will say the arcs shown here are produced when the capacitors discharge, so that they will give their energy into a target which is heated to a temperature that is higher than 210⁹ Kelvin. Okay, then when actually in the lab you can do that easily, like see that discharge. Just charge a capacitor and then connect the two what's called lead, and then they're gonna produce these sparks. Now, most of capacitors have something between the plates. We call it dielectric, so that they will be able to store more energy. These dielectrics, they are non-conducting material, and some of them, they are using long strips of metal foil for the plate, separated by strips of plastic sheets, just as mylar, or different materials. Now, when we have the dielectric connected across a charged capacitor, the charge, it is Q on both plates, and the potential difference is V0 when it is without the dielectric. When we insert an uncharged sheet of dielectric, like paraffin, glass, Teflon, like we will solve in the problem, polystyrene, between the plates, the potential difference decreases to a smaller value V. This is because of the induced charge that will be created on the dielectric, and therefore is going to make the voltage, the total voltage, decrease, and Q, it's not unchanged. Therefore, the C, which is the capacitance, the ability of it to store charges, is increased with the dielectric. Now, this is a comparison between two situations, where on the left I have only vacuum, on the right I have dielectric. when a dielectric is inserted between the plates of a capacitor, we will find that the electric field will decrease, and this is due to the polarization that is really for the dielectric, which induce an electric field like this is the positive is going to induce a negative charge here on the dielectric, and the negative is going to induce a positive, and therefore the total electric field is going to be less because of that, I will say, induced electric field. Now, when an insulating material is inserted between the plates of a capacitor whose original capacitance is C0, the new capacitance, it is increased or is greater by K, which is called the dielectric constant. And then C equals K times C0, and that is K times epsilon 0 A over D. This is for a parallel plate. And the energy density in a capacitor also increases by a factor of K. Now, the permittivity, now we call it K times epsilon 0, where it is the dielectric times the electric constant. Some of the dielectric constants are really here listed for different materials. We consider a vacuum as 1, and also air to some extent is 1 because it is 1.00059. Teflon, which we will use it in one of the examples, is 2.1, and here different materials. Of course, here, if the electric field is strong enough, the electric breakdown occurs and the dielectric becomes a conductor, and the dielectric strength is the maximum electric field the material can withstand before breaking down occurs. Then there is like a maximum, electric field. For example, here we are using Pyrex glass, has a dielectric constant of 4.7 and a dielectric strength of E maximum here, EM. That is 110⁷ volts per meter. Dry air has a dielectric constant of 1.00059, and dielectric of E maximum is going to be 3×10⁶ volts per meter. Now here, this is like just talking about some kind of why we have that polarization. Some molecules, such as H2O, N2O, because they are really, they have a big difference in electronegativity. If you look at hydrogen, it is far to the left in the periodic table, and oxygen, let's say, in the middle, and therefore they're gonna have difference in their electronegativity, and that is gonna make, for example, in H2O, oxygen is gonna have, although it is sharing, is gonna bring the electrons more towards the oxygen, and this is gonna cause a partial, I will say, charge to be created, and therefore we call these polar molecules. When no electric field is present in a gas or a liquid with polar molecules, the molecules are oriented randomly. But if we are going to have an electric field, they tend to orient themselves as in B, depending on the direction of the magnetic field, of the electric field. They're gonna align with it. And even a molecule that is not ordinarily polar becomes a dipole when it is placed in an electric field, because the electric field is gonna push the positive charges in the direction that is of the field, and pushes the negative away in the opposite direction. And then they have induced dipoles, and therefore we are going to have what is called polarization of molecules within the dielectric, leads to the formation of a layer of charge on each surface, and therefore is going to create a charge density of magnitude, which is, we call it maybe sigma I. And therefore, this is gonna have, of course, kind of a resultant field that is occurring from the difference between the two fields. One of them is the actual electric field between the plates here, and the other one is the induced one. Now, a neutral sphere also attracted to a charged sphere is going to be always also creating induced charges because of polarization. It is like here you can see that it has a positive charge, then that neutral object is going to have a negative next to the sphere, and the positives away, and therefore and you can see the I would say here we have attraction between this part and this part, and we have also here repulsion, and therefore we're gonna have the resultant of these two forces. Now, Gauss's law can be used for calculating electric fields in dielectrics. And here we are using a Gaussian surface that is a rectangular box that lies half in the conductor and half in the dielectric. And we can say the closed, integration of K times E dot dA equals Q enclosed free, the free charge enclosed by the surface, divided by epsilon 0. And Q enclosed free is the total free charge, not bound charge, enclosed by the Gaussian surface. And that is, again, we are going to use this in one of the examples. I'm gonna stop here, and then for the problem solving, I will have another session. Thank you and have a great day.